Mojtaba Ahmadieh Khanesar. I'm going to do my presentation on optical metrology devices for industrial robots, calibration using intelligent optimization approaches. So the work we have done in this project, we have used the laser trackers to actually calibrate industrial robots. So the table of content of my work is like this. As you can see here, we would have an overview of my work. Then methodology would be talked about, experimental setup, experimental results, and then we will talk about the conclusion. As you can see here, we have a laser tracker system. This laser tracker system is capable of doing 3D position measurements within a space, and the area it can cover is up to 60 meters. The accuracy of this device is 3 micrometer per meter, and it is actually a non-contact metrology device. So the way we have utilized this device, we have used it to actually calibrate the dimensions of the industrial robot, in this case UR5, which there is, as you can see here, there is a laser target on the device. We are measuring the movements of the industrial robot, and then using the feedback provided by the laser tracker, we are able to actually calibrate the dimensions of the industrial robot. So as you can see here, the industrial robot forward kinematic suffers from some uncertainties. The uncertainty which is assumed in this presentation is the uncertainty associated with the dimension of the industrial robot. So as you can see here, to obtain the position and orientation of an industrial robot, it is required to consider the parameters of the industrial robot. So these parameters are called DH parameters, then weight Hottenberg parameters of the industrial robot. Using these parameters and the forward kinematic of the industrial robot, it is possible to find the position and orientation of the end effector, as well as all of the joints within the 3D space. As you can see here, this industrial robot is a collaborative robot, is a cobot. So it is capable of moving around, and it uses some special algorithms to avoid collision and ease its programming. The forward kinematic of the industrial robot, as you can see here, finds out the relationship between consequent links of the industrial robot, and then finally by multiplying all of the transformation matrices in all of the links, it is possible to find out the transformation matrix associated with the end effector of the industrial robot. There are 4 different parameters which identify the forward kinematic of the industrial robot. QI are the joint angles of the industrial robot. DI, the link offset. AI are the link lengths. And then we have link twist, which is identified by alpha I, which actually shows the different parameters of the DH parameters of the industrial robot. And all of these parameters are used within the forward kinematic to identify the position and orientation of the industrial robot. As you can see here, the mathematical relationship from one link to another is identified using this transformation matrix. So we have QI as the joint angles, alpha I as the twist, link twist, as well as the other parameters like AI and DI. All of them together identify the forward kinematic of the industrial robot from one link to another. And then to find the overall forward kinematic of the industrial robot, it is possible to multiply all of these forward kinematics to each other to find out the overall forward kinematic of the industrial robot. So the way we have calibrated the industrial robot DH parameters, we found out the position of the industrial robot using the forward kinematic, as well as the feedback which is provided by the laser tracker. Of course, these two types of parameters are in two different coordinates. We need to find a coordinate transfer to actually convert the coordinate of the forward kinematic of the industrial robot to the coordinate of the laser tracker. And then we actually find the error between the positions which are given by the forward kinematic as well as the positions given by the laser tracker. Of course, with having some different trials on the different DH parameters of the industrial robot, it is possible to find different positions for the positions according to the forward kinematic of the industrial robot. Then if we optimize this error, it is possible to find the optimal DH parameters of the industrial robot to make this error as minimum as possible. So in order to do that, we have used different intelligent optimization algorithm. The first intelligent optimization algorithm which we have used in this study is artificial bee colony. As you can see here, artificial bee colony is a swarm-based optimization approach, which is based on the movement of bees within environment to find the optimal place of the food. Using a similar approach, it is possible to do optimization on the DH parameters of the industrial robot. As you can see here, a summary of this algorithm is given. And then the next algorithm which we are using is the gravitational search algorithm. Gravitational search algorithm is basically based on the interaction between masses. So a mass with better cost function is given a bigger mass value. In this case, this mass actually absorbs all other masses, and then all other masses are pushed toward the best mass, and then they scan overall space to find out the best position for the optimization. The best position then is associated with the unknowns of the problem. As you can see here, a summary of this algorithm is also given. We have acceleration terms which are proportional to forces between the mass, and the mass with a higher mass value, it can absorb the other smaller mass. Then we have velocity according to acceleration, and then we have position according to velocity. In this way, all of the masses actually scan the whole world, whole actually problem space, and then the optimal value for the unknowns of the problems are obtained using this method. So in order to perform this algorithm, as I mentioned earlier, we have used laser tracker. The laser tracker, the specification associated with this laser tracker are given here. As you can see here, it can perform position measurement. It is complying with ISO certification, ISO 17025. It benefits from Wi-Fi and LAN capability, so that's how it communicates with PC, and we can gather information from it. We have operated this laser tracker under 10 Hertz to gather information, and the distance from the robot to the laser tracker was 2.8 meter, almost 2.8 meter. And the industrial robot which we have used in this case is a universal robot UR5. As you can see here, this universal robot, its weight is 18.4 kilogram. It is capable of moving 5 kilogram load. Its reach is 85 centimeter. And then we have a joint range of 360 on all of the joint, plus minus 360. The speed of this robot is 180 per second, 180 degrees per second. Of course, we usually operate it with much less speed, but that's the maximum speed. Like you can see also other parameters associated with UR5 in this slide. So using the artificial bee colony optimization algorithm as well as gravitational search algorithm, it is possible to find the DH parameters to reduce the mean absolute error from 70.2 micrometer from uncalibrated points to 55.2 micrometer for ABC algorithm, artificial bee colony algorithm, and 56.0 for gravitational search algorithm. This is, of course, for trained data. In case of test data, we have 75.4 micrometer, which is by using the optimization algorithm, it reduces to 60.9 micrometer for gravitational search algorithm and 60.1 micrometer for artificial bee colony. In terms of speed of convergence, as you can see in the figure, the speed of convergence for artificial bee colony algorithm is faster than gravitational search algorithm. That's why we prefer artificial bee colony as the preferred optimization algorithm. As you can see here in 3 different dimensions of X and Y and Z, you can see the calibrated values. As you can see here, the laser tracker values are the reference point, which are the more precise values, and then we have uncalibrated values. They are the position values as obtained using the manufacturer given parameters. Of course, these manufacturer given parameters are correct for all universal robot manufactured by Universal Robot, but in case of our specific industrial robot, there is a calibration which we have done using ABC algorithm as well as gravitational search algorithm, which we can see it is much closer to the blue line given by the laser tracker than the uncalibrated version. In the 2D space, XY as well as XZ space, as you can see here, we have better points. Laser tracker points are given by red, and then ABC algorithm are given by black, which shows that using the calibration algorithm of artificial bee colony, it is possible to have position measurement which is much closer to the real values given by the laser tracker. So in conclusion, what we have done in this project, we have used the laser tracker to do 3D position measurement. Using these measurements from the laser tracker, it is possible to find out more accurate DH parameters for the industrial robot. The optimization algorithm which we have used in this project is ABC, artificial bee colony algorithm, and using this artificial bee colony optimization, it is possible to reduce the values of the mean absolute error from 75.4 micrometer to 60.1 micrometer for the test data. And yeah, this project is of course supported by EPSRC Harrison project, and we acknowledge this project content. Thank you so much for your attention.
Okay,